So we wanted to learn a couple of things. One, how does accelerating flow at an angle in a nozzle affect boundary layer growth? And how does boundary layer growth affect the velocity of the flow?
Our literature research efforts did not reveal a significant amount of information directly associated with subsonic viscous flows and boundary layer formation within a convergent nozzle. There were some basic ideas that are summarized above. The negative pressure gradient will inhibit separation from the wall. The accelerating fluid will thin the boundary layer, as detailed in the following slides, and the turbulent transition will be delayed.
So in this picture, it shows couette flow, which is where the top plate is moving. It's a way of simulating boundary layers. This is useful to know because on the right side you can see that the pressure gradient is less than 0, it's negative, and this is what's happening in a nozzle. That's a negative pressure gradient causes the flow to accelerate through a nozzle. And it also shows the effect on the boundary layer, how it becomes more elongated versus separating like it would in an adverse pressure gradient. And then this picture here on the right also shows the effect of higher Reynolds numbers, which in a nozzle, the Reynolds numbers are constantly increasing because of the constricted flow. And what this does is it causes the boundary layer to shrink. And so this was something that serves to counteract the usual trend of boundary layers growing over the length of an object. In a nozzle, the reverse can happen because of this effect right here.
As a basic analytical solution, we iteratively solved for the velocity, boundary layer displacement thickness, and mass flow rate in a given nozzle. To resolve the boundary layer, we used a flat plate solution to approximate the development of the layer. The solution process discretized the nozzle and calculated the mainstream fluid velocity at each point based on the compressible flow mass balance equation, assuming a choked flow at the exit. Armed with the fluid velocity and location in the nozzle, we calculated the boundary layer displacement thickness. The boundary layer was assumed to constrict the area of fluid flow, so we would repeat the calculation until the velocities, areas, directly related to the displacement thickness, and mass flow had converged throughout the nozzle. We also carried out some CFD simulations to verify our analytical results. We simulated 3 different straight converging nozzles of small, medium, and large exit areas. Some of the results for the nozzle of the small exit area are presented here. The analytical displacement thickness compared to the CFD obtained displacement thickness is shown in the graphic on the left, while the Mach number distribution of the airflow in the nozzle is presented on the right. The analytical displacement thickness has a somewhat similar shape to the CFD solution, but the magnitude is some 3 to 4 times larger than the CFD result. Note the sudden change in the analytical displacement thickness close to the exit is a result of the laminar to turbulent transition. Now we have changed the images on the right to reflect the pressure distribution in the nozzle, both for the entirety of the nozzle, the inset, and then the region nearest the exit. The almost monochrome nozzle reflects the negligible changes in the pressure across the majority of the nozzle, indicating that the pressure gradient does not play a significant factor on the boundary layer for the majority of the nozzle. The mass flow is also fairly low across the majority of the nozzle, but the angle of the impinging flow is fairly high. Unfortunately, the results from the second CFD simulation, that of the medium exit area, are hobbled by some computing errors that have prevented a complete analysis of the displacement thickness for the CFD solution. From what we can see, the analytical and numerical solutions do not agree for the obtained CFD displacement thicknesses, differing both in shape and magnitude. Now the magnitude appears to be off by an order of magnitude, with the analytical solution continuing to increase the thickness of the boundary layer while the CFD predicts decreasing boundary layer displacement thickness. We also note in the image on the right the accelerating velocity of the main flow shown by the colored contours. Again in this image we have the accelerating flow near the exit with the boundary layer near the wall. The image at the right represents the pressure distribution through the nozzle. Now the region of significant pressure gradient has grown to include half of the length of the nozzle, but the angle and acceleration of the flow has decreased somewhat compared to the first scenario. The last scenario is the one of the largest exit area. The analytical and numerical solutions are again compared on the left, with the first half of the nozzle witnessing a comparative match in the shape of the 2 curves, while the latter half of the nozzle sees a reduction in the CFD displacement thickness while the analytical solution continues to grow. Again, Some errors prevented us from obtaining results for the CFD displacement thicknesses in some areas, but we assume that they smoothly fill the vacancy across the CFD results. Also note the much higher velocities across the nozzle, inducing turbulence much earlier in the analytic solution. This time we note that the exit Mach numbers for the 3 CFD simulations is negligibly smaller than 1, indicating that the boundary layer has little effect on the mainstream flow speed. And finally, an examination of the pressure distribution across the nozzle reveals that there are pressure gradients across the entire length rather than just a region near the exit. But compared to the other two scenarios, the angle of the flow is much less than the first case, while the magnitude of the flow is much greater.
So we faced a couple of challenges in our project. One of them, the biggest one, was probably iteration. We had to, in order to solve analytically, we needed to start with an area ratio, solve for velocity, plug that back in to find another area ratio, and keep iterating until we found the right thing. And it included a lot of factors, which made it difficult as well. And you'll see that on the next slide. We also started with too broad of a scope initially, and eventually had to cut it down to what we did today. And finally, we weren't able to find a specific answer to our first question, which was how angled flow and accelerating flow influence boundary layer growth. We know that they do, and we could see it in the preceding images of our data, but it's not exactly clear what exactly would model that. Some of the factors that went into this were compressibility, effects of temperature on speed of sound and dynamic viscosity. Viscosity we just held constant, but speed of sound had to be iterated on because of the change in temperature and vice versa. The effect of angled flow. Again, in the previous problems we could see that due to both angle and acceleration that the boundary layer was suppressed later on, but the exact relationship we don't know. Negative pressure gradient was also a major factor. And finally, the laminar to turbulent transition is totally different than it is from a flat plate in external flow and internal flow because of the unique conditions in a nozzle as we've explained. Some of those are pressure gradient, angles, increasing Reynolds number. All those make that a very different experience.